And hi. Would be interesting seminar. Hi, Frank. Just a moment. Stop transcription because we do not need transcription. Okay. So it's 2:01 and we can start our seminar. As many other seminars, it's very exciting, and I'm very happy that Jose is he's with us today and will present his brand new results. Talk about himself a little bit, about what he is doing and what his group. Just in short, now Jose is the outstanding researcher and scientist, but also he is good in organizing. He organized EuroMER conference in 2016, as I remember, and it was I believe not only me but many others. I still remember that. And he is now associate editor of the Journal of Fluid Mechanics.
Yes, it's true.
And
yes.
that is the main journal for us. So that is the very exciting to have a member of Journal of Fluid Mechanics explaining us how to what means good research and what the possible to do in such, I could say, classical problem as droplets, impact, and Leidenfrost. So that is the, it seems like from textbook, but the progress is possible, and some such progress will be presented by Jose. By the way, about this presentation, please mute your microphones, all of our participants, and if you switch off your camera, it would be helpful. So then I will switch my camera as well, and I mute my microphone, but I will be here. And if you have a question, please either just ask, either write in your question in chat, and then I will transmit to the speaker. So, okay, Jose, the floor is yours.
Okay, thank you so much, Alexander, for this very nice introduction. Thanks to all of you for attending to this talk. I must express my thanks to Professor Koropkin for his very kind invitation to participate in these applied research seminars. And today, well, before talking about this paper we just published a couple of weeks ago with Guillaume Riboux, I will just say that we are a very small group. It's basically Juan Fernandez, Guillaume Riboux, Paula, who is a PhD student, and Francisco, who just incorporated. And we are interested in microfluidics, bubbles, drops, and we try to do experiments and model our observations doing both numerical and theoretical approaches. And today I will talk about the impact of a drop on a isothermal or a superheated substrate with applications to the dynamic Leidenfrost regime. And before just going into details into the main point of this presentation, let me first refresh your minds and see these pictures, which clearly reflect what the Leidenfrost regime is when we place a liquid mass over a superheated substrate. Let me first define the superheat as the temperature difference between the substrate temperature minus the boiling temperature of the liquid. If this value of the superheat is sufficiently large, then as you can see here, is that drops do not touch the solid but levitate over a very thin stable vapor layer. And in this case, in these very nice pictures, in this annual review by David Queret, we can see that this stable vapor layer is about 100 micron width. And one of the main consequences of the existence of this lubricating vapor layer is that, as we see every day when we pour some oil, for instance, in a heated saucepan, and then we slightly incline the saucepan, then what we can see is that this drops slide very rapidly, and this is a consequence of the fact that the liquid is evaporating. There exists a very thin stable vapor layer which decreases the friction between the solid and the drop. And one of the main consequences of the Leidenfrost regime in technical applications is that due to the fact that the thermal conductivity of the vapor is much smaller than that of the liquid, then this vapor layer acts as a thermal insulator. And in applications when we want to cool down very rapidly a heated solid, then what we do is to submerge this solid into a liquid bath. And our purpose is to cool it down as fast as possible, and then what we expect is that as the wall superheat increases, the wall heat flux increases, as we can see here. But the thing is that if the solid is too hot, then what happens is that a stable vapor layer forms, and since it acts as a thermal insulator, then as you can see here, the heat flux decreases, and this is undesirable for applications. Another manifestation of the Leidenfrost effect is when we place a drop over a heated substrate, as we saw in the previous slide, and we measure the drop evaporation time. If we plot this drop evaporation time as a function of the wall superheat, we can see that, as expected, this evaporation time decreases with the superheat, but it reaches a minimum, as you can see here, and after this minimum coincides with the appearance of a vapor layer which starts insulating the liquid from the solid. So whenever this vapor layer exists, the heat transfer process is limited, and then from a technological point of view, many industrial processes try to avoid the Leidenfrost regime, which is analogous to say avoid the existence of a stable vapor layer, because the wall heat flux is reduced and the evaporation time is increased, as you can see here. One of the ways to avoid the existence of the Leidenfrost regime is to use roughened solids, because in this way, when the height of the protuberances is of the order of the thickness of the vapor layer, what happens is that the stability of this vapor layer is destroyed, then causing the contact between the solid and the liquid. And when this contact is produced, then locally the liquid wets the solid, and then this enhances the heat transfer. This is what can be seen in these beautiful experiments in this paper in 2009, where the authors first heat a sphere and then suddenly submerge it into a liquid pool which is contaminated by nanoparticles. And what they observe is that when these nanoparticles cluster and cluster over the surface of the solid, and their sizes, the total size of this cluster of particles becomes of the order of the thickness of the vapor layer, then as you can see here, the evaporation time, the cooling time is notably decreased, just to 1/2. So disturbing the stability of the vapor layer favors the that the heat flux increases, and because the contact between the liquid and the solid is produced as soon as this vapor layer is destroyed. This is an important aspect that we will refer in a few minutes. And another way to, so from a practical point of view, what is important is to increase the Leidenfrost temperature, which is defined as the minimum temperature of the solid for which a stable vapor layer exists. So if we increase the Leidenfrost temperature, then we will have a very large range of temperatures for which the contact between the solid and the liquid is produced, and then the heat transfer, the heat flux between the solid and the liquid is large, and then we cool down the solid very rapidly. So what we want to do is to increase the Leidenfrost temperature in applications, just to promote the fast cooling down of solids. One of the ways is using rough solids, rough substrates, in order to disturb the vapor layer. And another way to do that is precisely to, instead of using static liquids, to just let the liquid move towards the heated wall. And this is known as a dynamic Leidenfrost regime. It's when we do in practice that to cool down a solid, what we do is to direct a jet or drops of liquid. This is the spray cooling mechanism. We direct the liquid not with a negligible velocity, but with a velocity different from zero to the heated wall. And in this way, we will favor the heat transfer from the liquid to the solid, increasing the Leidenfrost temperature, as we will see in a minute. These very illuminating and interesting experiments from this viral paper in 2016 by Shirota, Limbeck, Chaosum, Andrea Prosperetti, and Detlef Lose, is that they use as a solid sapphire, which possesses a very large thermal conductivity, and this is important for experiments in order to experiments that reveal the physics behind this process. The idea of using this type of solid is that due to the very large thermal conductivity, during the impact process, the solid does not cool down, and then the temperature of the solid substrate remains mostly constant, because sapphire possesses thermal conductivity of the order of that of steel, with the advantage that it's transparent. And they use TIR, the total internal reflection method, to determine when the liquid touches the drop. This experimental technique consists in that when the laser beam, when the liquid touches the wall, the laser beam is refracted into the liquid, but if there exists a very thin gas or vapor layer between the drop and the solid, then the beam will be reflected and it will be recorded by a high-speed camera, and then we can see these images in which we can see that blues mean large distances. Well, large, over 200 nanometers. So, but there exists a distance between the liquid and the solid, or smaller distances, which are these reddish colors here on the perimeter of the impacting drop, as you can see here. But these experiments reveal that in the case there was a contact between the liquid and the solid, that would be produced at this perimeter, but not in the center, as you can see here, because the distance is of the order of 100, 200 nanometers or more. These experiments also reveal that when the contact is not produced, the shape of the vapor layer is not, the thickness of the vapor layer is not uniform. It's larger at the center than at a certain distance from the axis of symmetry of the drop. And here, what we can see is from this same reference, Shirota et al., from this epiral paper, what you can see here is that taking an ethanol drop with a millimetric ethanol drop impacting at a constant velocity, okay, what happens if we increase the solid substrate temperature. So what we can see is that the boiling temperature of ethanol is 78 degrees. So we are in this experiment 70 degrees above the boiling temperature. The superheat is 70 degrees. Then we can see that the liquid for this impact velocity contacts the solid. This black indicates, this black color indicates that the laser beam is being refracted into the liquid, so it's not being reflected and captured by the high-speed camera. But when we increase the temperature, the solid temperature, what we can see is that this contact is prevented. The larger the superheat, the less area is contacted, the less liquid area contacts the solid. And when we reach the Leidenfrost temperature, 220 degrees for this impact velocity, what we find is that the liquid never touches the wall. As you can see here, these blue colors here indicate that there exists a gap. I think that this blue you can see here indicates that there exists a gap of at least 80 nanometers between the liquid and the gas for all values of the radius. So here we can see that Shirota et al. They also measured what's the minimum value of the substrate temperature for to avoid the complete contact between the liquid and the solid. And as we anticipated, and our intuition and experience indicates, the larger the impact velocity, the larger is the Leidenfrost temperature, which is favorable for applications. The larger the Leidenfrost temperature, the better will be for applications, because we will have a larger range of temperatures for which the heat flux is large. Large meaning that we avoid the existence of a stable vapor layer, which, as I repeat the idea, isolates thermally the liquid from the solid. So in this interesting paper, the authors, Shirota et al., they also found that it's also common to the impact of drops over isothermal substrates. The fact that the drop is impacting a solid, then this process entraps a gas bubble at the center of the drop with, you can see here, HD. So HD here, you can see this HD here is the height of this bubble, and the height of this bubble at the center, at the axis of symmetry, scales with the Stokes number, defined as the density of the liquid, the impact velocity, the radius of the drop, divided by the viscosity of air. Okay. So as it's proportional to the Stokes number to -2/3. This is a very well-known scaling, which can be very easily deduced by just balancing the overpressure needed to decelerate the liquid with the overpressure needed to make the lubrication thin gas layer flow radially outward. So it's very well-known in these papers by Mandre and Bohuis, and previously by the theoretical framework presented by Frank Smith. This is very well known from decades, and it's also this bubble is a very slender bubble, because the characteristic length, the radial extension, is a square root of HDR. So this is a very slender bubble. And what we can see is that the minimum distance separating the liquid from the solid, which is the important point in our presentation, because we want to determine how the Leidenfrost temperature depends on the impact velocity of the drop. This is the topic of this talk. We are interested in scaling, which is the minimum thickness of the vapor layer, this HM that I'm representing here. But this HM was not reported in this 2016 paper. The only thing that was said in this paper is that, as we can see here, these experimental points correspond to the radial distance where H-min is reached. And what the authors found is that this this radial distance evolves with time as the square root of 3 tau, with tau the dimensionless time, and it corresponds to the wetting velocity of a drop impacting a solid, which we deduced a few years ago, Guillaume and I, in this paper where we describe the splashing of drops. And now the topic of this talk will be to try to find out how HM scales with the control parameters, assuming that the solid possesses a very large thermal conductivity, so that the temperature of the solids it does not vary during the impact process. The results for those cases in which the thermal conductivity is not that large can be done by just taking into account the growth of the thermal boundary layer in the liquid. A thermal boundary layer in the solid, using ideas similar to those I will talk now. But so now our purpose will be to scale HM as we already know HD, which is this thickness. What's the thickness of HM, with the purpose of determining the minimum substrate temperature for which there exists a gap between the solid and the liquid. Now we turn to another very interesting paper by also the group of Detlef Losse. In this very interesting paper published a year ago, this paper by Chantelot and Losse, where they report both HD and HM, the minimum thickness at the square root of 3 tau. They report both for different values of the impact velocities. They focus on the case of ethanol, and this we will also focus on the case of ethanol, which is a liquid for which we have more experimental information to describe this dynamic Leidenfrost regime. And what they found is that indeed the thickness of the gas bubble entrapped at the center of the drop indeed scales as 2.8 radius of the drop times Stokes minus 2/3. And as you can see here, HD varies depending on the impact velocity from 5 microns to 1 micron. And here they also measure, very interestingly, they also measure as a function of the impact velocity, which is the minimum thickness at a square root of 3 tau. And as you can see here, these distances vary from 1 micron to 200 nanometers. And they cannot, now I will turn to this question later, they cannot measure smaller values of HM below 200 nanometers. And they also find that the dependence of HM with the impact velocity is also of the type Stokes 2 minus alpha, with alpha larger than 2/3. This, as you can see here, this slope is clearly larger than this. And our purpose here will be to understand these experiments reported recently by Chantelot and Losse. They also reported the very interesting question which explains why we cannot measure thicknesses below 200 nanometers, because when the drop impacts, they also observe that the liquid locally contacts the solid at some nucleation points, and at these nucleation points then there exists a wetting front, this black area that we can see here, where the light is being refracted into the liquid, and then the vapor layer is already destabilized in the azimuthal direction and provoking the contact, the short-time contact between the solid and the liquid. And the reason why this contact is produced is because of contamination. They report experiments for exactly the same drop, exactly the same impact velocity, exactly the same temperature, and sometimes they measure that the contact is produced when the distance, the minimum thickness of the vapor film is 200 nanometers, other times 400 nanometers, because it depends on the presence of solid particles on either the liquid or the solid. whenever the vapor layer thickness becomes of the order of these asperities, then the contact is produced, inhibiting the or destabilizing the vapor layer, and then breaking the Leidenfrost regime, provoking the contact between the solid and the liquid. They also measured the conditions for which short-time contact is produced, a short-time contact due to this type of events, depending on the impact velocity. They measure these red points, and as we can see here, by this line which separates the region where we have short-time contact from the region for which we do not have contact. For a given impact velocity, as you can see, we have contact, but if we increase sufficiently the temperature, then the thickness of the vapor layer will be larger than the typical size of the particles, of the dust particles present on either the liquid surface or the solid surface. And now, with all this information, we will try to scale HM as a function of the control parameters of this physical situation. And we also, for our modeling purposes, we also make use of these experiments in Chantelot losse, which reveal that in the area, in the wetted area, let's say wetted area, no, I mean in the area comprised between square root of 3 tau to the axis of symmetry, what we can see is that the radial vertical velocities of the thickness of this vapor layer is much smaller than the impact velocity of the liquid. What we can see here is that the typical velocities of the vapor layer in this region, if this is a square root of 3t and this is r equals 0, the typical vertical velocities of this vapor layer are much smaller than the impact velocity of the liquid. What we can see in these experiments is that these vertical velocities of the vapor layer are practically of the order of millimeters per second, and this impact velocity is of the order of 1 meter per second. And then our simplification will be to consider that when the drop approaches the wall, is as if the liquid impacted the wall, a rigid wall, with small relative errors. That this is our main assumption, and then we will see if this assumption, based on this experimental information, that the vertical velocities of this vapor layer is much smaller than the impact velocity of the drop, we will see if this provides us with good results or not. And then this framework, theoretical framework, is the one that I will describe in the next slide, and it resorts very much on this, what we wrote a few years ago in this paper. And these ideas are very familiar to Alexander, of course. In 2013, he visited our group. He presented his famous work on the leaping of cats, how cats drink, and he introduced to us to all these beautiful mathematical techniques and theoretical frameworks based on the Wagner theory. And we were really, since we teach aerodynamics, we were very used to the linearization of the boundary conditions, which are usually done in aerodynamics due to Prandtl and Glauer, and to the study of aerotational flows. And then, since locally the drop is a parabola, very near the wall, what we can is linearize the local shape of the parabola to that of the plane Z equals 0, as we can see here, committing very small errors. So the solid contact, I mean, the region where we impose the impenetrability condition is this region that we can see here. This is the free interface, and far from the wall, what we can see here is Z equals 0, which is, this is the wall, and this is locally the parabolic shape of the drop, which is falling, but since it's a parabola, you can linearize the boundary condition and then say that it's located approximately at z equals 0, and then solve the Laplace equation subjected to the impenetrability condition here, committing errors of the order of relative errors of this order. It's not a solid contact, but the velocities of the vapor layer are very small compared to the impact velocity of the liquid. So the velocities far from the wall needs to be equal to those of to that of the liquid falling over the substrate, and for values of the radius larger than the area where the contact is being produced, this region here is the region where the region of interest for the study of the dynamic Leidenfrost regime. This very tiny region around here, exactly is the boundary separating the region where we have the thin vapor layer and the free surface. And the Euler-Bernoulli equation, since we are interested in short times after contact, Euler-Bernoulli equation tells us that with small relative errors in tau, the instants of time after touchdown we are trying to describe are very small, then we can approximate the solution of the Euler-Bernoulli equation to phi equals 0. This means the potential is equal to the value of the potential at t equals 0. If we solve this problem, which is is analogous to the one originally solved by Wagner, but in a slightly different geometry, because this is a disk of radius and non-radius. We see here, if we solve the Laplace equation, then we find that the vertical velocities here can be found analytically like this. This solution can be found in papers by Alexander or in Lamb as well. And then with this velocity, if we make use of the time-integrated kinematic boundary condition, namely a point located at a distance a from the axis of symmetry, what's the time for which this point will reach z equals 0, will touch the wall. This time-integrated kinematic boundary condition, which is the so-called Wagner condition, provides us with the expression relating the weighted radius with the time after contact, which provides us with this square root of 3 tau. And this is known, and it's also known that due to the impact between the liquid and the wall, then there exist very large tangential velocities to the wall that diverge near the contact point, near square root of 3 tau, diverge as the square root of a divided by x. This form of the potential near this region is very well known from aerodynamics. It's the type of flow describing the flow around the leading edge of an airfoil at an angle of attack, and it can be easily deduced by finding the local solution of the Laplace equation into the in a wedge of angle 2 pi. It's very well known. And then the thing is that since these tangential velocities diverge as x to minus 1/2, then we would have here a velocities tending to infinity. But of course, tangential velocities to the vapor bubble do not tend to infinity in the vicinity of a square root of 3 tau. Why? Because it can be understood that if we move with radially outwards with in a frame of reference, moving at a prime, okay, at the wetting velocity, with the velocity at which the liquid is wetting the solid, then what we see is that in this relative frame of reference, what we have is velocities coming from the right towards the axis of symmetry with a velocity a prime. The liquid is flowing towards the left with in this moving frame of reference with velocity a prime, but at the same time the tangential velocity is diverging as x to minus 1/2. So in this moving frame of reference there must exist a stagnation point at a distance xs given by the solution of this equation. So xs varies as a, which varies as tau to the 1/2 divided by a prime squared, and a prime varies as the derivative of this, which is tau minus 1/2. So this width, which is tiny, this width varies with time as t tau to the 3/2, and this wetted area is tau to the 1/2. So this is a very, very small region where, and this is an interesting thing, where here it will be useful for our purposes to describe the flow in a moving frame of reference, because in this moving frame of reference we have this stagnation point of the flow, and in this very narrow region there exists a very large pressure variation, because we have a maximum of pressure in this point, and if we move towards the center of the drop, there the pressures are much smaller. So in this region of characteristic width xs, we will have a very large pressure variations, which indicate that the pressure gradient in this small region is huge, and this is the main idea behind the scaling that I will present next. But first, let's summarize what we have found in the frame of reference moving with this velocity, which varies as tau to minus 1/2. There exists a region of characteristic width xs, which is proportional to tau to the 3/2. See also this paper by Skolan and Koropkin, where the pressure changes from its maximum value. This is just Euler-Bernoulli because the flow is quasi-steady, and then you can see here how pressures diverge as tau minus 1, velocities as tau to minus 1/2, and therefore the characteristic pressure gradient is delta P divided by the width where this pressure variation takes place. So it varies as tau minus 5/2. So the pressure gradients are really huge and would tend to infinity, but of course neither velocities nor pressure gradients tend to infinity, because there exists a minimum value of tau. This value of tau is a characteristic time at which the bubble is entrapped, because the liquid does not immediately touches the wall, because as we described previously, a bubble is entrapped at the center of the drop. So which is the minimum value of tau, where this description I have presented you is valid, because we need to describe, if we want to find which are the most demanding conditions for which a stable vapor layer exists, is when this pressure gradient and this pressure and these velocities are the largest, and those will occur exactly when the bubble is formed. The bubble entrapped at the center of the drop is formed, and this occurs at a time scale tau m, which is nothing but the thickness of the bubble entrapped divided by the impact velocity. And then, so this provides us immediately with the scaling a constant times Stokes minus 2/3, using our result of HD with this constant 12.4 was very kindly provided to us by Chantelot and Losse. So introducing this value of tau m into this expression, and this expression, then what we find is that the maximum tangential velocity that we find during the impact process is this, varies with this as Stokes to the 1/3. The maximum overpressure varies as Stokes to the 2/3, and the minimum, so the width of the region where pressure variations takes place varies as Stokes to -1. The values of the Stokes number are of the order of 10 to the 5 or 10 to the 6. So you can see here why this width is of the order of 100 nanometers. It's really, really tiny. and these overpressures can be of the order of 1 atmosphere or more, so 10 to the 5 pascals, due to this a very large factor for impact velocities of the order of 1 meter per second. And now that we have described this, then we move to the ideas of lubrication. So we have a region where we have a very strong pressure gradient, and in order for the liquid does not touch the wall, what we need is that there exists a finite vapor layer with a finite thickness that separates the liquid from the wall and avoids the contact between the liquid and the solid. And all we need to do is to we will see later that the ideas behind lubrication theory can be well applied, because all this process is dominated by diffusion from the point of view of the gas. So lubrication theory is it dominates the flow of this very thin vapor layer with these thicknesses of the order of 100 nanometers. And then what we have is that the addition of I'm moving in a frame of reference. Let me remind you that I'm moving in a frame of reference, moving at the wetting velocity, at this wetting velocity. So the wall is moving to the left with the wetting velocity, and then we have these very large pressure gradients from the stagnation point to the pressures at the center, which are much, much smaller, but these pressure variations take place at the characteristic thickness HAM, which is excess what we found previously. And this addition, Couette plus Poisson flow, needs to be equal to the flow rate of vapor, which is produced in this very narrow region, which is the one closest to the wall, where due to the very large temperature difference between the solid, which possesses a temperature above the boiling temperature of the liquid, and the liquid, which is at the boiling temperature, here there exists a very a temperature difference in a very small distance. So the heat flux is the heat flux through the vapor layer is large, and all this heat flux is dedicated to evaporate the liquid, and this evaporation of liquid this vapor which is produced here is flowing towards the center of the bubble. So now all we need to find is an expression relating the flow rate per unit length of vapor produced in this region, which is flowing towards the center of the bubble, and this will provide us with an expression for HM, okay, which is our unknown. So how to model the flow rate per unit length of vapor? So as I said previously, so all this process is dominated by diffusion, and the Prandtl number of the vapor is of order unity. So the Reynolds number times the thickness of the vapor layer divided by the width of the region we are interested in this in describing. So Reynolds times the thickness of the layer divided by the width of this region is this parameter beta, and this beta, which is the thermal conductivity of the vapor times the superheat divided by the viscosity of the vapor and the latent heat of ethanol, this number here is usually smaller than 1. So this means that in the end, in spite of you could have a small entrance region where velocity profiles could be uniform, but they will rapidly, so viscous diffusion will rapidly dominate the flow. So inertial effects in the gas can be neglected in a first approach, and also thermal in the energy equation. So the energy equation is dominated by the conductive term. And then we have approximately a linear velocity profiles of temperature in this very thin region. And then we can compute the heat flux in this very easy way. This is what Sobak and colleagues did in 2014. And then if we neglect the heat flux from the liquid surface towards the inside of the liquid through a small thermal boundary layer, which can be demonstrated that this flux from the evaporating interface to the liquid is small. Then if we assume that all the heat flux from the wall to the liquid is dedicated to evaporate the liquid, this permits us to calculate which is the flow rate of vapor produced in this very thin region of characteristic with HAM, this XS. Now we have this, then all we need to do is to substitute the value of Q of the flow rate per unit length of vapor, and then solve for this quartic equation for HM, which is a quadratic equation for this variable Y, which is defined like this. And then we simply solve this quadratic equation and find the solution that HM is, as you can see here, C tau is a number that was provided to us by Chantelot and Losse, and all these material properties and Stokes number. As you can see, we have a close equation for HM, and we compare the experimental data of Chantelot and Losse with our prediction, and we have no fitting constants here. We have the experimental data of Chantelot and Losse, and our prediction is there exist deviations of the order, maximum deviations of the order of 30%. And let me comment to you how we did this calculation. We did not fit any constant, and we used real material properties of the fluids. We evaluated the material properties at the mean temperature between the solid temperature and the boiling temperature of the liquid, which is the temperature of the evaporating interface. And we use the real material properties, and we use real material properties of air and ethanol taken from tables. And we had to, of course, make use of the relationships of how the viscosities, densities, etc., depend on temperature, which is not trivial. So you really need to take the real material properties of the fluid to if you really want to calculate this without any fitting constants. You have to evaluate the vapor density, taking into account that the vapor produced at in this region where pressures are very large, at the densities, taking into account the ideal law of gases, and evaluating the density of the vapor produced at the mean pressure of this region where the pressures are the higher, the stagnation point pressures. And in order to calculate this beta, which appears here, so here you have the viscosity of the vapor, but of course the viscosity of the vapor, it's better to make appear the Prandtl number, which does not depend on temperature, and then the heat capacity of the vapor at constant pressure, which we can express in this way, taking the tabulated tables of ethanol. And of course, you also need to take into account which is the dependence of the viscosity of the vapor and the with temperature, and the viscosity of with temperature, which this for real fluids you really cannot resort on the kinetic theory of gases, but you really need to take the tabulated data, which can be easily accessed through the many tables existing in the literature, which can be accessed also by just Googling it. And as another check of our prediction is that, as I commented to you previously, Chantelot and Losse provided us with the conditions for which we had short-time contact. This short-time contact depends very much on the presence of impurities or asperities on the surfaces of either the drop or the solid. And let me remind you that what Chantelot and Losse told us is that the sizes of these irregularities is in between 200 and 400 nanometers. And then what we said is, okay, what we are going to do is to make use of our equation, but now Y is known. The thickness of the vapor layer, if you want to determine when the contact is produced, is equal to the thickness of the impurity, let's say 200, 400 nanometers, and then we find directly beta, and finding beta means finding which is the substrate temperature for which we would have the first contact between the liquid and the solid. And what we find is that if we make use of these values of the asperities of the particles, dust particles that could be present in experiments between 250 nanometers and 360 nanometers, what we can see is that both the experiments by Chantelot and Losse and also the experimental data by this group who did experiments using another technique, which is fast X-ray imaging, which correspond to these two black dots. Our predictions, depending on the size of the impurity, is in reasonable agreement. We cannot exactly predict because it depends on the contamination present at each experiment. But as you can see, our prediction for these usual values found in experiments is, when we compare, is good between our predictions and the experimental data. But now what we find is that, okay, you say this is a way to predict which is a Leidenfrost temperature, which is the minimum temperature for which we would avoid the contact between the solid and the liquid. But what we find is that this paper, which is by Chirota et al., which is the one which motivated our study, it happens that predicts Leidenfrost temperatures which are smaller. Let's say you can see here 2 meters per second, 220 degrees, and for 2 meters per second, the Leidenfrost temperature for which that you would the solid temperature that you would need for the liquid not to contact the solid at this very thin region, where the distance between the gas and the solid, this HM, is really large. It's really large. So the conclusion we reached is that the spatial resolution in the experiments by Shirota is not as good as in these other experiments, because if you really want to avoid the contact at every radial position from r equals 0 to r equals the square root of 3 tau, including this very thin nanometric region of width xs, which depends as Stokes minus 1, if you want to do that, then the result of the substrate temperature is this. This would be very large velocities, but for applications, does it really make sense to predict this temperature? And in fact, it doesn't, because if what you want to do is to determine which is the minimum substrate temperature for which the heat flux is reduced, it's simply it would be enough that you avoid the contact in all the radial extension of the bubble, except in a very narrow region where contact could be produced. But this narrow region of width, typical width, HAM, I mean Stokes minus 1, are radius of the drop, Stokes minus 1, nanometric region, of the order of 100 nanometer region, you could have contact there, but the heat flux in this region And this contact is really in this area is very small. So you can consider that you already have the Leidenfrost regime when you really have a bubble at the center, and then you allow local contact at a distance square root of 3t from the axis of symmetry. So we interpret the data of Chirota et al. As those conditions for which you have a big vapor bubble at the center, but there doesn't exist a vapor layer here because the liquid touches the wall. And so but these conditions, which are not as demanding as these, are the real interesting conditions for applications, because the existence of a very large vapor bubble at the center of the drop is what limits the heat flux between the wall and the liquid, and then it's our purpose to try and predict these experiments by Chirota et al. Under the hypothesis that a vapor bubble is produced at the center, but local contact can be produced at the square root of 3 tau from the axis of symmetry. And then what we do is simply that this vapor bubble will exist whenever the vapor produced at the center. So what we have here is the area of the area of the wetted region, times the width of this cylinder, the time derivative of this volume. The time derivative of this volume, this is the volumetric growth rate of the vapor bubble, of a vapor bubble of constant height hd, which is the thickness of the vapor bubble entrapped at the center. So we need to feed all this growing volume by vapor, and this vapor comes mainly from the central area of this cylinder of with a circular radius, square root of 3 tau. Then, because we can show that the amount of vapor produced where the distance is minimum in this region, contact region, square root of 3 tau, is very small when compared to the amount of vapor produced right at the center of the bubble. Then if we just equate this times the density of the vapor equal to the vapor produced by evaporation, we obtain simply this equation, where we calculate the density of the vapor, taking into account that, of course, the vapor is at a temperature different from the atmospheric one, and we simply obtain this provides us with the minimum value of the substrate temperature for which we produce enough vapor so that we can feed the growth of this growing volume of vapor beneath the drop. This provides us with this equation, and this is our prediction. Where we did not fit any constant, and here we have maximum errors of the order of 15% for the larger impact velocities. We need to take into account that we use real material properties evaluated at the mean temperature. Of course, things are a bit different from this, but this is an approximation. And also, we also have to take into account that at the center of this vapor bubble we have air and ethanol, and so we really don't know the exact composition of this mixture of air and ethanol at the center of the bubble. But in spite of these approximations, we think that our prediction is could be used for applications where you need at least an estimation of what the Leidenfrost temperature will be as a function of the impact velocity. I thank you very much for your attention, but let me finally say that for the case in which we do not have this is isothermal substrate, then we make use of the same ideas as before, but and then we solve this equation. Then we solve this equation. But since in the isothermal case, let's say ethanol drop on not superheated substrate, this QV is in the instead of the vapor produced, this is the flow rate of air in the moving frame of reference coming into this thin region, which would be VMHM. And so just solving the same type of equation, a quadratic equation, we also have the a prediction for the width of the thickness, the minimum thickness of the air layer in isothermal substrates, and without any fitting constants. So what we have is that the comparison with published data is good. Okay, thank you very much. Thank you for your patience. Thank you very much to all of you, and I will be happy to answer any question you may have.
Thank
Hello.
you very much. I understand we are behind 1 hour, so some participants left, but still many of our participants, they have time to stay, as I understand from the list of participants who are with us now. So any questions, please? So we can stay longer, no problem with that. Any questions? Any questions from this moment? Yeah, Peter. Yes, I was looking for you. Yes, please.
Thank
Peter.
you, Sasha, and thank you for a very nice talk. It was really interesting. I was wondering about the slow speed limit of your dynamic Leidenfrost behavior. Because if there's a paper by Detlef Loos for the air cushioning problem, which balances the inertial speed against surface tension, and there's a maximum size of your bubble in the middle. Now that determines a velocity scale at which point the pressure you induce by inertia becomes less important than surface tension. If you put that velocity scale into your prediction of dynamic Leidenfrost temperature against velocity, does that then give you a prediction for a non-dynamic Leidenfrost temperature? Because that's the point at which your inertia is then balanced by surface tension.
Yeah, and this is so can you see this slide or not?
The slide is gone.
No.
I have to share. So it's this, it's this, and it's this. Okay, so here you can see this a black line. These experiments were taken.
Could you make a full screen, please?
Full screen, yes. This black line corresponds to what Peter was mentioning. When the speed is not that large, what happens is that the overpressure in the stagnation point is compensated by capillary pressure. And in the paper, what we describe is the length scale, which is not HAM, so Stokes -1 is not Stokes -1, but the characteristic width where pressure variations takes place is exactly the one in which the capillary pressure, which is sigma, which is a surface tension, a second derivative of the interface, which is HM divided by an unknown length LM squared of the order of the delta PM, which is the overpressure, caused by the stagnation point. And then this by balancing the overpressure with the capillary pressure, then you find which this new Lm is, which is not the width deduced by Wagner's theory, but by just balancing overpressure with capillarity. And then you make use of this equation, but the pressure gradient takes place in the new length Lm, which you obtain by balancing the overpressure with the scale where the curvature, the length scale, the radial length scale, where the curvature of the interface is produced, and then this you just substitute this HAM by the new Lm deduced from the balance of capillary pressure, similar to the overpressure caused by the stagnation point. And then you just solve the lubrication equation. This, you can see here, this equal to VNHM. Just solve it with the new length, which is the one in which pressure variations will take place, and then you obtain this. And then these vertical lines that you can see here is just a transition when you have to use either the capillary balance, which is this capillary balance is small values of velocity. This is for ethanol, this orange line. This black line is for water. As you can see, for water, you have to take the capillary balance. And so for large values of the velocity, you will always have the inertial regime. And for smaller values of the impact velocity, you enter into the capillary regime, which conceptually simply changes the length in which pressure variations takes place. And then you make use of lubrication. So it's the same physical idea, changing HAM by LM. Have I answered the question?
I think so, yeah. But I just want to ask, does that put it to a static Leidenfrost temperature then, rather than a dynamic Leidenfrost temperature? Because there is no impact velocity ultimately.
No. So when the velocity tends to zero, but Peter, this is important that when I started reading about this around a year ago, and then you see the velocities here, 0.2 meters per second, and then you wonder how this experiment is done, because I don't know how to what's static, because 0.2 meters per second is I mean, it's difficult to control. So this is if you wanted to do it static, I think that it's difficult to do it with less than 0.2 meters per second.
I can tell you how it was done.
Okay,
Yep.
tell us.
We just hang the droplet and we move the substrate towards it.
Okay, with a very small velocity, yeah.
Okay.
Because it's difficult when you drop it.
Yeah. Thank you, Departamento. Thank you. But so the static limit, in fact, if you want to do this experimental realization, is not. So you really have to design on purpose an experiment. So I'm thinking more on applications. If you want to cool down something, what you do is you just spray a surface, or just and then velocities are usually larger.
Yeah. Any other questions, please? Any other questions? I have a list of questions. I can ask. So first of all, it's about is the velocity of the droplet is constant in your calculations?
If you is you mean if we have varied, well, the Stokes number is varied, but
no. Did you account for with the time speed of the droplet is getting smaller and smaller, and finally it's approach the static position? No.
So we just take the approach that at infinity the velocity is u fixed in time.
Okay. Okay. So this means that potentially, if you start from impact, and finally, what we can imagine, it will be a static position of the droplet with the very thin layer, right, between the droplet and the substrate. But you actually consider the initial stage, right?
Yeah. So it's the
Not
let's say the short time contact because we think that these are let's say the most difficult conditions because it's when the pressure gradients are the largest, and so the most difficult conditions to avoid the contact between the liquid and the solid. So we from the beginning we understood these were the most difficult conditions, and then we decided to work on the conditions where the pressure gradients are the largest.
Okay, understand. Devaraj, you have a comment.
Yes, well, a question actually. So there's one thing that I didn't completely understand, and that is so you said basically you would expect in the Shirota experiments that the temperature, the Leidenfrost temperature, would be much higher, but they could not simply resolve, if I understood correctly, the basically the minimum. Is that just because in the TIR experiments simply the resolution wasn't large enough to really see that? Or
this is the only explanation I have for this, because both experiments are done exactly with the same experimental technique.
Yeah.
And you have these experiments with two different experimental techniques, fast X-ray and TIR. Then what we would expect for, let's say, 1.5 meters per second is temperatures of the order of 500 degrees.
Yeah.
And in these others, 200 degrees. Then the only thing that because both experiments are done with the same material, everything, and then the only explanation I could find is that whereas the ones on the left by Chantelot and Losse and by Lee et al. Really looked at the very finer details of the flow in the region where pressures are larger, and they took lots of care in describing this region. Here, maybe the resolution was not that large, and then they simply saw a larger area, which in fact from an experimental point of view and from applications, I think that the data on the right is the most important one, because it's when you have enough heat flux to produce enough vapor to fill in this growing volume, which in fact it's exactly what you commented in your talk 2 or 3 weeks ago. So you need to fill in this growing area, and it really doesn't matter if you have local contact there.
Yes. Yeah.
Really
I get it. Yeah. Thank you.
You are very welcome, Devaraj.
Yeah, and could be the very last question, but it's not really a question. It's yeah, but I still should ask. How about oblique impact?
Sorry.
Oblique impact, when the droplet is not vertically, not in normal, but at angle, could be in potentially could we expect that there will be no contact between the droplet and the substrate because of that, but it will be ricochet from the surface without contacting it, or like in problems with air cushioning, the air cushioning is very problematic, say, if the impact is oblique. And there are almost no such thing as the air cushioning and that thin layer. So what's your comment on it? I'm not sure that you did it, but yeah, potentially it's very interesting because like cooling with a normal impact, as you said, it could be problematic. But cooling with the oblique impact could be potentially possible.
Yeah, so the thing is, I think that the best way to describe this is in a frame of reference, moving with the tangential velocity of the drop, and then we have already in the same equations that we have here, we have for the wet flow we have Vm plus the because and Vm is described with the normal velocity, so it's Vm plus the tangential component of the velocity, but the equation is the same. We only have to do in the right part Vm plus tangential velocity times Hm, and in the left part we simply need to describe the motion in this moving in a frame of reference, moving with the tangential component of the velocity, and then we repeat the algebra. But I guess that since Vm is much larger than the tangential component, usually in applications at the tangential velocity of a falling drop, maybe the term dominating everything is Vm instead of the V cos the angle at which it's falling. I guess. And then I think that everything could be repeated just taking into account in the relative frame of reference, taking into account that the world is moving is already moving to the left with the tangential component of the drop.
Yeah, that is what you are saying. What you are saying, it's a hydrodynamic part of the problem. So in terms of hydrodynamic, in terms of that polar flow, yeah, I do understand what change should be introduced. However, I'm more concerned because it could be because I'm not so familiar with that. I'm concerned with the thermodynamical part. So because if the droplet come to new part of the substrate, which is still on kind of another temperature. So the temperature under the droplet and temperature of substrate outside droplet, I believe they are different between because there is that evaporation, right? So how to account that? Possibly the thermodynamic is not important. But
so I really because I really do not see, because an observer moving with the tangential velocity of the drop, so it sees this, but unless the velocity of the drop is huge, the tangential velocity of the drop is huge. There is, because from a thermodynamic point of view, the internal energy only enters into the equation when it's so I mean that the kinetic energy of the relative flow never enters, and so I don't know how. So the important thing, I think, it's hydrodynamically, and I think that I don't think it's much more difficult than this. Describing it into this relative frame of reference, I think that it's mostly the same. Maybe I'm wrong, but
yeah. Okay.
This is
okay. I see. So as it's now only kind of specialist in this topic remain in our meeting, but we are almost 20 minutes behind. So I suggest that we thank Jose. Thank you very much, Jose, for a very interesting presentation.
Thank you. Thank you so much to you, Alexander.
Yeah, I hope the people who didn't understand full details, they can look at your recent paper. It's just recently published, but also to watch this video with and to stop that slides where you discussed details of your analysis, details of your experiments. I found that at least I should watch this seminar again because it seems to me that it's there are some ideas which are quite deep and they resonate with the talk by Devarash. And if we put this talk together, then there could be.
So the point is, there are many similarities indeed because of the cutoff time. AUM is the same as the Devarash said, and I think that the idea is we are very close friends, and it seems that we think similarly. It doesn't matter that we don't.
But from different directions.
In different directions, yes.
Not you are not going the same way, so that is good because you can think alike, but they are kind of supplementary to each other, or complementary, supplementary. But it's if to think in the same way, it would be too boring.
Exactly.
It's true.
Definitely, definitely it's different, but in some sense, this is you are attacking the same direction and the same problem, and you are going, you are thinking in the same way. That is. This is indeed important, and there is a very interesting ideas I got from Devarash and from you. So very good, very good. So thank you very much, and I stop recording.
Aha, I can see you now.
Thank you, guys.
Finally,
I have to run because the people from my next meeting are all here. So
okay.